So today we continue with our series on control. We had speakers from UC Santa Barbara, now it's me, Daniel Hill, a couple of weeks ago. And we continue today with the topic of control, which is related to something all of you are interested in, is energy. And so we hear something that just goes beyond just an field of control. We are in fact fortunate to have today Professor John Ching from the University of Southern California, Department of Chemical Engineering. Professor Ching is also an appointed, besides being an endowed chair professor at USC, University of Southern California, he is also has an honorary position with one of the most famous universities in China, Tsinghua. And he, in fact, got his undergraduate and master degree from that university, Tsinghua, before coming to this country, getting his PhD in Chemical Engineering University of Maryland. And he was on the faculty of the University of Texas, Austin, until about 3 years ago, when he joined the University of Southern California. Today he will speak about optimal feedback strategy for building demand response control. Please welcome Professor John Ching.
Thank you, Professor Benny, for inviting me for this seminar. It's great to come over, drive from about 1 hour time to get to another university to give a talk. So this is a really nice, good opportunity for me to visit you guys here. So I'll pick up this topic today because I think it's interesting to a lot of the current, most important engineering problems we are facing, and I'm going to show a little bit more later. You'll see why it is important. And I have my co-author list up here, which is basically the PhD student who are working on this problem. So he did most of the work, so I recognize his name here. For myself, as Professor Benny introduced, I have sort of a mixed background as in electrical engineering or control, and then into chemical engineering, and then being professor within chemical engineering, now also jointly appointed between chemical engineering and electrical engineering. So now those are the two departments I'm associated with, and both of them are named after some big alumni donors, so they're very nice to us. We're trying to keep that trend going. Okay, I will go through the introduction for what is demand response. You probably, if you have not been into the smart grid domain or that area, you may need a little bit explanation about what is demand response. And from the control point of view, we think that is actually a control issue. And then the project, we're getting into the project structure and where we need to get the model, which is system identification, and then optimization and control. Then I'll summarize and give some future things we want to do. So this is one of the flowcharts for energy that's consumed inside the United States. Has anybody seen this slide before? Okay, maybe then this is good. I can spend a few minutes to explain it. What's on the left is you will see just where you get the primary sources of energy, like nuclear sort of imports, and then you got sort of natural gas, you got coal, and then the others are from petroleum. Basically, these are the sort of the oil portion there. These are huge. All the sources we're consuming every year, and the overall consumption is that much, about 100 extra joules. Okay. So then you can see this. A good portion of that, about 40% of the primary energy is going into the conversion to electricity. And we know that when you convert thermal energy or other energy into electricity, you lose a lot, okay? Because of the second law of thermodynamics, you only have a part of that being generated, converted into electricity, and a big part actually of sort of going into the waste or to some really this is the energy loss. So for whatever the current technology we have now, we cannot convert more than 50% of the primary energy into electricity. So that's one issue there. But we have to use electricity because it's easy to distribute and convert to other things. And this is the sort of the sectors that are consuming part of electricity or heating or other raw material as feedstock to the chemical and petrochemical industries. You can see how the energy are consumed at that level. So you get about over 100 extra joules, and then you get about 27, 20, and then 20 as for each portion there. And there's the 320s do not add to 100, right? So there's a big portion that's wasted, and the waste is mostly due to the energy conversion issue that you have to convert from the primary energy into electricity there. So this is the big picture we're looking at. And now what you see here on the left side, the supply side, we got petroleum, we got coal, we got other things, but we don't have the renewables, the wind energy, solar energy yet. So that's the picture around 2002 or so. When people talk about energy issues or energy crisis, they always bring up these balances, like, okay, you have to supply the total amount that's required for the consumption side. Now, for us, the control and electrical engineers, we also have to look into another factor. It's not just the total sum that has to be balanced. You have to balance it minute by minute or every hour. I'll explain why that has to be the case. This is a picture of the electricity consumption in California. This is about around the year 2000. For the entire year, you can see how the electricity is consumed. Okay, there's periodic up and downs here. It's probably corresponding. It is corresponding to the weekly cycles. Okay, so every weekend there's less consumption than the weekdays, and you can see that for the summer 3 months, there's much higher consumption of electricity than the other months. And within this summer 3 months, you get peak load every week. Right? Every week it reaches peak, and that's where you can tear down the grid. If everybody is turning off your air conditioning and use other things as well, then you could tear down the grid, and that could be a big problem. So it's very important to make sure that during the peak hours, we do not consume more than the whole power generation capacity can generate. And that is not an annual balance, it's not a monthly balance, it's not a daily balance. It has to be balanced minute by minute because we don't have a good way to store electricity. You cannot generate it 3 hours ago and then use it 3 hours later. So we do not simply have a good power storage for electricity. We could store other energy sources, but not electricity. So okay, not to the scale that we would like to have. So that brings up an issue. That is, how can we handle this? Handle the user side or the consumer side so that we not only have to make sure we don't tear down the grid, but also we make it easy for the power generation so that we can get the best design efficiency out of the power generation, and also that will save energy, right? And also make sure they don't have to build that many power plants that's just in the standby mode. Not all the power plants are running 24 hours a day. Some of them have to be shutting down for most of the day, and then only for 3 hours they turn on. They're turned on. So that is, if you can minimize that, trying to make sure that your consumption or the demand is more constant, then it's a lot of you're doing a good deal for the power generation and distribution there. Okay. So let's look at sort of a particular date. This is in the summer, August the 16th of that summer. You'll find what are the major contributors to that peak hour consumption, right? On the leftmost bar, that is the commercial buildings, buildings air conditioning. Okay, that's the 15%. And then next to it is 14%, that's for residential air conditioning. Okay, so you can add up, just during the peak hours, it's almost 30% is consumed due to air conditioning. Of course, you get also this 11%, which is the third most consumed portion, that is commercial lighting. Okay, it's not hard to figure out if you want to regulate the demand during the summer days. Okay, air conditioning is the most important thing to look at. So if we can manage somehow the demand or the usage of air conditioning, especially during the summertime, then we're helping the grid, we're saving energy and also saving the money there. So that sort of brings up the topic for today. So to do that, there has to be a sort of coordination or some communications between the generation side and the demand side or the consumer side. So the way you talk to each other, now there's almost no talk. You just plug in you turn on your air conditioner, you plug in something to use electricity, it's all the same, right? There's no difference between what time you use it and so on. You pay the same price. Now, for larger users, like industrial users, they have different pricing strategies now. Okay, it's not always the same price for any time during the day. They actually would charge you not only just on the total consumption of energy, but also on what's the maximum use for 15 minutes, okay, or some small time interval. What's the peak hour usage or peak usage of electricity? So they would charge the large users for two portions. One is based on how much power you're consuming overall. Okay, the other part is called demand. And that is the maximum peak use during the day or during a week or a month. So you do have two portions that you pay for. The basic price on the cumulative usage, and also another charge on top of that you pay for the demand charge. So the cumulative use is something you perhaps have to consume, and then the peak hour is something you can regulate. If you can somehow average your usage during the day, then you're saving money. You're helping the grid, helping the generation side. Okay, so this is the communication from the generation side. Okay, they set up a pricing strategy to sort of make sure that you respond to it. Okay, so if there is no price difference, then you would not care to respond. Now you can, you do, because if you can somehow minimize the peak hour use, you will pay less price. Okay, so that is when the communication starts between the generation side and the consumer side. That's where I think you can see why the smart grid is necessary. So there's another factor I think that is very important for us to look at now. That is the primary sources of energy needs to be renewable. This is also in the California in the state regulation, and by 2030 or something, there has to be a certain portion of electricity that's generated from the renewables. So when you get into the sort of the solar energy, like this one here, you get the wind or those renewable sources. That's part of the electricity provided through the grid. And then there's additional complexity there. We can step back and think about what was the case before. When you had coal and natural gas and other things to generate power, those energy were stored there in the form of coal. They are very stable. Okay, if you don't burn them, it's not going to release anything. So you can decide how much coal you want to throw into the power plant. Okay, you generate